Okay, ich starte dann mal. Good morning, everybody. Let's allow a few seconds so everybody can log in. We're still waiting for a few more people to join. All right now. Good morning, everybody, or good afternoon, depending on where you are. And welcome to our webinar on multi-selectivity stationary phases. My name is Guido Krautz. I'm the Business Development Manager at Dr. Maisch, and I'm the host of this meeting today. Before we start, I have to do some technical announcements. According to GDPR guidelines, I need to make you aware that this webinar will be video recorded. Your names will not be visible to other participants unless you ask questions using your name during the question and answer session. I assume that you consent to these conditions. Otherwise, I need to ask you to leave the meeting now, but I hope you don't. Now, your microphones will stay muted throughout this presentation. You have the opportunity to ask questions during the question and answer session after the presentation, and you have two ways to do so. You can ask questions in writing. In order to do that, please click at the question and answer icon at the bottom of your screen and type your question, and I will read it out so our speaker can answer your question. Alternatively, you can raise your hand, again, using the icon at the bottom of your screen, and then I will unmute your phone and you can speak up and ask your questions. Now, let me introduce our speaker today, who's Dr. Jürgen Meyer-Rosenkranz, Product Manager at Dr. Maisch. And once again, he will speak about multi-selectivity stationary phases. All right, Jürgen, it's your turn now.
Okay, thank you for the introduction, Guido. Yeah, okay, let me share the screen. Oops. Okay, yeah, as Guido has already mentioned, today I want to speak about multi-selectivity stationary phases, which is one of the most modern approaches to develop methods in HPLC. When we speaking about selectivity, then it's the selectivity means that the interactions between the sample molecule and the surface of the stationary phase, and these interactions are supported by the mobile phase. So therefore, we have to look on the sample molecules, how we are looking are, and the other thing is, of course, that we are looking to the surface of the stationary phase. And the third point is how will the mobile phase support these interactions? Our main focus of course, is the reverse phase chromatography, because that's the most used chromatographic technique in the world. It's around 70%. And if we look about the possible interactions, we have about 6 different interactions which are possible. And the lipophilic, the green one, that's of course, the best known. Everybody knows about that because that's the basic interaction which is based on the technology, of course, yeah. And then we have 5 different polar interactions which are not so well known by the users, but they are also pretty important for the method development, and also if you have some issues and want to go forward to change interactions, they are really playing a big role. What we have is the different dipole interactions. So we have the dipole induced dipole interactions, and of course the hydrogen bonding interactions. What's also becoming more and more important is the p-complex bonding interactions that are in the phenyl rings or have the p electrons, and later on I will speak about that. And at last one we have the cation exchange. Yeah, so we have, depending on the stationary phase, we have always 6 possible interactions. And some stationary phases are supporting this one. Some stationary phases are supporting only a few of those interactions. Let's go to the different stationary phases to look which interactions they can support and which not. When we're speaking about multi-selectivity, that means that the stationary phase offers different possibilities for the interactions, and of course, to support and to increase selectivity. If we are looking to the first set of stationary phases, they have a balance between the lipophilic character, mainly presented through with C18 or C8, and we have polar groups on the surface. So we have a lipophilic polar balance where the molecules can interact with it. So if we are looking to the C18 phases, the one possibility is to use a non-eincapped C18 phases. So we have, beside the non-polar C18 groups, we have also silanol groups available, which are able to make these polar interactions. That's the first. The other possibility is to go to a C8 phase, and the C8 phase has 2 possibilities of interaction. Of course, the C8 group, which is the lipophilic interaction, which is lower as the C18, of course, but also due to the fact that the alkyl chain is shorter, the interaction to the backbone to the silanol groups is has a higher possibility, and therefore there are more polar interactions on the C8 phase. And the third one is the phenyl phases, which has, beside the lipophilic interactions, the p electron system, which also offers a polar possibility. One of the most sold and most used columns with a lipophilic polar balance is the AQ, the aqueous phases, or HE for hydrophilic end capping. And there we have beside the C18 groups, we have a polar group on the surface, which offers the polar interaction for polar molecules. Beside that, we have the EPS. EPS is means enhanced polar selectivity, and that's it's not clearly defined what EPS is. It depends from the different manufacturers, and it can be that there is there's a low carbon level, so we have more silanol groups, or the other possibility would be that there is a amide or carbamate group in the alkyl chain. So there are different possibilities. At the end, it means that there's an additional polar group on the surface to the alkyl chains. And then we have the typical short chain phases, which can be also used in straight phase chromatography, but also in reverse phase. And if you're using it in the reverse phase chromatography, you have the possibility to use the lipophilic interaction. That would be for the cyano and the amino, the short C3 chain, the propyl chain. And for the diol, we have also a short alkyl chain, which allows the reverse phase interactions, and the polar groups, they are offering the polar interactions. So going to the next group, I already mentioned that the phenyl phases, they have the p electron system, and so we have a balance between the lipophilic and the p electron interactions. And today there are a lot of different phenyl phases available. At first we have the propyl one, propyl phenyl, the hexyl phenyl, and then we have the biphenyl, where we have two phenyl rings in a chain. And it's different to the diphenyl, where we have two rings directly on the surface. We will come later to that, what the strength of these different phases. Then we have a mixture from the C18 phenyl, and also what's a pretty interesting phase is the C18 PFP. PFP means the pentafluorophenyl, and of course, it's also available as a pure PFP phase. Yeah. So let's go to the third block of phases. There we have the lipophilic ion exchange balance. Typically, they are called mixed mode phases because they are offering the reverse phase interactions by an alkyl chain or a phenyl group, or by a cation exchange or anion exchange group. So what we typically have is a alkyl chain C18 or C8 combined with a anion exchanger or a cation exchanger. And it's also possible that instead of an alkyl chain, we have the phenyl ring, and also we have the strong cation exchange group on it. Also, what we have the typical ion exchange phases, like the propyl sulfonic acid. That's due to the spacer, we have here a C3 chain, so we have also here a reverse phase interaction, and additionally the cation exchange interactions from the sulfonic acid. And we have it similar, but the other way around, because it's a basic group, the amino group. We have here a strong anion exchanger combined with a C3 group. And the last block are the helic phases. The helic phases is that they have beside the polar interactions, which are the base of the helic methods, we have a lot of different additional possible interactions depending on the stationary phase you are choosing. For helic, it's a little bit more complicated because a lot of the phases are only called helic phases, and it's not clear what chemistry is behind that. And it will be, I will only have a short touch to the helic phases because that will be a complete webinar itself. What we have is, of course, that we can use the bare silica, for example, which has the polar groups from the silica surface, but also the silanol groups has also the possibility to act as a strong cation exchanger. So also here you have two possibilities, the polar interaction and the ion exchange interaction. And depending on what you are using, you can use different possibility for this stationary phase. And you have always to be aware which kind of interactions you have to go straight forward with your method development. So let's look to some chromatograms. We have here a test mix which was developed by Ultrasep some years ago, and that's our special compounds which gives you a feedback about your surface chemistry. We have here now 3 different ReproSil pure stationary phases, and we have the AQ type, we have the ODS3, and we have the not end-capped version of the ODS3. And as we see here, we have, of course, different chromatograms. Let's look at about the compounds which are in here. At first, we have URacil, that's a dead volume marker, and of course, it's for all 3 columns at the same point. And the second peak is a strong acidic compound. It's para-hydroxybenzoic acid. And what we're seeing here is that we have, for the more polar phase, for the AQ and the not end-capped, we see that we have here a slightly more space between the peaks. We see here more baseline. So what we are seeing is that the hydroxybenzoic acid, they taking these additional polar interactions from these 2 phases to get more retention. The same we see also the peak number 3, that's a diphenylhydramine, which is a strong base hit, and also we see a clearly more retention than for the other compounds. The same we can also see for peak number 5 at diazepam. Diazepam is on a standard C18 here at around 20 minutes. And if we are switching to a column which are offering a polar interaction, the diazepam take this interaction. And so we have an additional interaction which leads to a higher retention times. And we see it on the AQ phase here, but also we see it on the non-end-capped phase. Yeah. So if we are make it in a graphical view, we have here in the middle the red squares. That's are the standard C18, our ODS3 phase, and that's set to 100%. And now we have here in the green ones, that's are the not end-capped phase. And what we are seeing is that the not end-capped have always an increased key value, so it has more retention than on the standard C18, especially for all the compounds which has a polar group. So what we're seeing here is, that's pretty important, our stationary phase offering a polar interaction, and our polar molecules, they can exchange with that interaction. If we are going to the last compound, the toluene here, and it's a purely hydrophobic molecule, and what we're seeing here, that has nearly no influence on it, because it has no polar interactions. It has only interaction with the C18 groups, and the C18 groups are pretty much the same. So the level of the interactions are pretty much the same. Looking to the AQ type, what we are seeing here is that on the AQ type, that we see that the most polar compound has the highest additional interactions. And if we are going to the increase in hydrophobic character of the compound, we see that the interactions going low. And if we are going to the toluene, we see that the interactions are going to negative values, because the interaction with the hydrophobic molecule is lower. Yeah. So if we are going back to the chromatogram, we see that here pretty clearly. If we are showing to the toluene, we see on the AQ phase, the retention of the toluene is lower than on the 2 other phases. And what we are seeing here also, that is the toluene is pretty much at the same place, because the influence from the end capping on the toluene is pretty low. So So if you are looking here to this set on these 3 different columns, they have all a complete different selectivity. And that's the advantage for the end users in the lab. If we need more selectivity in the polar range, and they started with a standard C18, it's a pretty easy to use this, the identical method in the first step and test it how it looks on an AQ phase. And the second possibility would be, of course, to test it on a non-NCAP one. And then you have 3 different selectivities, which would help you to improve your selectivity and also to improve your method. So here is an overview about our stationary phases, and in this case, my focus is on the ReproSphere line. And what we are seeing here, we have 9 different C18 phases with different selectivities, and this helps the end users to choose the right column for their application, for the method development. And the first help for choosing the columns are the carbon load. Yeah, we have here it's all the ReproSphere 100, so it may have all the same surface, and if you have a pretty high carbon load, like here, this is 20% carbon, then it's pretty clear we have a very strong hydrophobic character. If we are going to a lower amount of carbon load, like here for the C18 Aqua, it's 12%. Yeah, it's obvious that we have here a stronger polar character, and this phase, of course, offers quite more polar interactions than all the other ones. Yeah. When we are going down, we have, of course, beside the C18 phases, the C8 phases, and then also all the different phenyl phases, the standard phenyl, the not NCAP, and then the phenyl hexyl phases, also in the NCAP, the not NCAP version, and then the modern D-phenyl and B-phenyl phases. Yeah, it's important to know that we here for the D-phenyl, both are in the directly bonded on the surface with 2 phenyl rings. So it's a little bit like a chair here, and here on the biphenyl, where the 2 rings are in a chain. Beside this alkyl and phenyl phases, we have also all the other ones, the short alkyl chains, and then all the diol ethylpyridine, which is mainly used for SFC, and also one of the most modern phases is the polyethyleneimine phases, which is can be used in a lot of different applications. You can use it for reverse phase chromatography, you can use it for Helic, and it's also pretty successfully used in SFC mode. And then, of course, the Helic phases and special phases on it. So we have a complete set of different selectivities in every product line we are producing, and that's a really good support for the end users. So if you are purchasing a column from us, the most of the column reverse phase columns are tested with a default test. Yeah, and if we are looking now here to the ReproSphere 100C18 and the ReproSphere 100C18 DE. DE means double NCAPed. You see that the chromatogram looks pretty much the same, and that's also obvious because the NCAPing has both are NCAPed, and so there's no big difference between these chromatograms. The double NCAPing leads to more stability. That is the main reason for the double NCAPing. So what we are seeing here is we have the URACIL again for the dead volume marker. We have the phenol as a polar compound. We have the toluamide. It's a compound with a good balance between lipophilic and polar interactions. and at least we have the toluene, which has only lipophilic interactions. So if we are going from the C18 group to the final, what we are seeing here is that the retention for the toluene is much lower, of course, but what we are seeing, we have a slightly increase of the retention for the toluamide. What we're seeing here, that's the polar interaction of the additional polar interaction of the toluamide with the final rings. So we have an increased retention. And on the pure final phase, what we're seeing here is we have a peak exchange. So the toluene is still here at the same position, but we have an additional increasing of the retention of the toluamide due to the additional p electron interactions of the surface. So what you can see here is if you're going from a C18 over C18 phenyl to a phenyl phases, you can adjust your peaks at the position you will need for the best selectivity for your application. So if you're what we typically do when we make method developments, we are controlling this change of the phases with the key values, and we put the key values in a graph, and so you can see clearly what are the difference of the stationary phases. We have a very big difference here on the toluene retention, and the C18s, of course, as expected, they have the highest retention. We have for the toluamide, we see an increase in retention due to more polar interactions on the stationary phase. Yeah, and for the phenol also we see additional polar interactions which are leading to a higher key value on the more polar phases. Also to see what would be the best choice of a column for a method development, I have prepared this graph. And typically a lot of chromatographic users, they are starting with a standard C18 phase because that's the most used column, and pretty often this standard C18 phase leads to success. But more and more, then the applications becomes more complicated and the problems are increasing. You need a column which has more selectivity. And here we have our ReproSil line. And if we are looking here to the blue one, the blue line is the standard ReproSil plus C18 column. And what we are seeing here is always the alpha value between two compounds. And here on the left side, we are on the more polar pairs, and on the right side we are on the more lipophilic pairs. So what we are seeing here is that the standard C18 is on the left side in the polar region. They have the lowest values, so the selectivity in the polar region is not so high. Going to the right side, to the more lipophilic area, we see that we have a high selectivity. Going to the C18 EPS, as I already mentioned, EPS means enhanced polar selectivity. We see that we have here the highest selectivity in the polar range here on the left side, but we have a very clearly lower selectivity on the lipophilic character. Going now to the ReproSil plus C18 PFP phase, which are offering polar selectivity and hydrophobic selectivity, we see that have already a good selectivity on the polar range, but it has also a pretty good selectivity on the lipophilic range. So that's a pretty modern column with a very good overall selectivity. And so a lot of end users, they don't start anymore with the standard C18. They are starting immediately with a column with such a very good overall selectivity, which allows to have in very early state a good way to success with such a column. Okay, let's go to the method development for the for this multi-selectivity phases. What are the possible strategies to make a method development? How to support with different interactions which are offered by the stationary phase? So at first, I want to go to the ion exchange chromatography, because a lot of the multi-selectivity phases are offering an ion exchange mode. And so it's important to understand how ion exchange chromatography is working. So here we have a typical ion exchange chromatogram. It's a weak cation exchanger, and typically how the elution is performed on an ion exchange media is that you are starting at a low concentration of buffer at a middle pH, here 6.4, and we have a 0.05 phosphate buffer, and then on B we have the high concentration, it's 10 times more, 0.5 molar phosphate buffer, and increasing the buffer concentration will lead to the elution of the, in this case, of the proteins of the cations. So that's a way how it's typically used. And if we are looking to this high buffer concentrations, that's not the mobile phase which is wanted in the modern chromatography, especially if you also want to use an ELSD detector or a mass detector, a mass spectral detector. Good. Switching to the more modern approach, that's pretty important, because this approach shows us that there is not only the traditional salt gradient for elution, we have also two other possibilities, and that's here the green one, the pH shift or pH gradient, which we have here, and we have here a shift from 2.9 to 4.0. And the other possibility is also to run a gradient of the organic modifier. So at the end, we have three possibilities. And if we are looking especially to the blue area here, to the organic modifier, we see that there's the organic modifier, that's exactly the same elution procedure which we are using in reverse phase chromatography. And the effect of the acetonitrile is that if we are increasing the acetonitrile concentration, the dissociation of the ions going back, and if you have loss dissociation, you have loss interactions, because you are reducing the charges of your molecule. If you have less charges, you have low retention, and so you are forcing the elution. So that, and knowing that or seeing this, that we have not only the salt gradient, offers us to use this mixed mode or multi-selectivity phases, which have a lipophilic and ion exchange group, quite more effective in the method development. So that's the first important effect. The second effect, what we have is the most of the reverse phase IX phases are bonded with the RP and the IX group. So the two different silanes are used, and you have a statistical distribution from these two groups over the surface. In the modern mixed mode phases, as we have the reverse phase and the IX group on one silane. So the reverse phase and the IX group has always exactly the same distance, and the sample molecule has exactly two interaction points, the lipophilic and the ionic, always in the same distance, and in this same spherical orientation. And this is that's a clearly defined interaction area, and this is goes already to the affinity chromatography, which has the highest selectivity. Yeah, so it's a clearly defined area where we can have a clearly defined interaction, and that's pretty helpful. The similar situation with the spherical interactions we have also on the final phases. Yeah, so as I already mentioned, we have 4 different or 5 different phenyl phases. At first, the propyl phases, and the propyl phase is important to know that the ring has no mobility on the surface, so it's always in the same orientation, and therefore there is also a clearly defined interaction possibility between the surface and your compound molecule. Going to the hexyl final, due to the longer chain to the spacer, we have a high mobility of the phenyl group, and that allows to get in contact in areas of the molecule which are with the propyl final not possible, yeah, due to the steric hindering. And so these 2 phases we have can have a complete different elution profile, and it's important to know that. Some of the manufacturers, they are saying that the hexyl final is the better phase, but that's not true. You never know which one is the better phase. It strongly depends on the application and your molecules you want to separate. Both phases are important, and both has their possibilities, and so there is no better one, yes, both can lead to success. And then we have the 2 phases with the 2 phenyl rings. We have the B-phenyl, where the 2 phenyl groups are in a chain. And also here, if it's on the surface, we have a clearly spherical orientation of 2 p-electron systems, which also gives you a maximum on selectivity, because they are always in the same distance and always the same orientation, and that's also pretty helpful. And we have the same on the D-phenyl phases, but it's the 2 phenyl groups, they have a tetrahedral angel. So all the 4 phases which you are looking here have, beside the lipophilic interaction and the polar p-electron interaction, they have also the spherical orientation, and so we have 3 possibilities for improve the selectivity and the separation. Good. Let's look about the strategies for how you can use your mobile phase to support your selectivity, and if we have a reverse phase interaction combined with an IX group, the first possibility is always to start with a low salt concentration and low organic concentration. So this, if you have low salt and low organic, you have a maximum retention for the reverse phase and for the IX groups, because low salt and low organic modifier doesn't lead to elution. So starting both together, you increasing slowly salt and slowly the organic, you have always both interactions going hand in hand. Yeah. So if you want to weighten the IX exchange interactions, you keep the salt concentration low, increasing only the organic modifier concentration. That keeps the IX interactions low and the reversed phase elevation is the preferred elevation at that moment, or you can do it also that IX and reverse phase going hand in hand. So you're increasing salt concentration and organic modifier at the same time. And so IX and reverse phase elution starts immediately and depends and leading to a different elution profile. So that's are the three possibilities to balance out the interactions between reverse phase and IX concentration. So the other possibility is also to change the organic modifier. So if you are using methanol as organic modifier, it supports the ion exchange interactions and also the dissociation, and therefore it leads to more retention for the compounds which have the ion exchange interactions. If we are switching to acetonitrile as an organic modifier, we have that reduces the ion exchange interactions because the dissociation going back, so we have less charges, and if we have a lower number of charges, we have a lower retention on it. Yeah. So if you want to support the ion exchange mechanism, you're going to methanol. If you want a little bit reduce the ion exchange interactions, you are switching to acetonitrile. I already have spoken about the situation of the charges on the surface and on the molecules, and it's pretty important that you are aware which situation you have on your stationary phases. In this example, I have used the aminopropyl phases, and if we are using this aminopropyl phases, then we have here if we have a low acetonitrile concentration here on the left-hand side in the green area, and that's a range between 0 and 40% of acetonitrile, we have here mainly reverse phase interactions, yeah, because we have a slightly lipophilic group, the propyl group, and we have a high amount of water, and that's a typical reverse phase situation. Going to a higher concentration of acetonitrile, we don't have any more a reverse phase situation because that the lipophilic character of the stationary phase is too low for this high organic concentrations. What we have here is we have a polar phase, the amino group, and we have a high concentration of acetonitrile, and therefore we have here a helic area. And therefore, if you're making method development on this very polar phases, you have always to be aware that you are not mixing these two areas. So if you are working in the reverse phase area, typically you stop at that range of 40 to 50% of acetonitrile. And for helic, it's important you don't go below the 50% of acetonitrile. And typically the highest amount is about 95, 97%. So beside this knowledge about the hydrophobicity of the phases, it's also important to have a fully overview about the charge situation. So if we have on the aminopropyl phase a pH of 3 to 7, then the amino phase is completely charged. Yeah, and if we have and so the behavior of the aminopropyl phase is like a strong anion exchanger. So if we have acidic molecules, we have beside the reverse phase interactions here on the left side or the helic interactions on the right side, we have an additional ion exchange interactions, and therefore we have here, like the red arrows showing, we have here additional retention. So for acidic compounds, the retention will increase. Going to a a higher amount of acetonitrile, the number of charges will go back, as I already mentioned, and therefore we have, of course, still anion exchange interactions, but due to the fact that we have a reduced number of charges, also this will be lower here on the right-hand side. If we are working with bases, then we have, of course, at the pH of 3 to 7, we have the same situation that the surface is positively charged. But if we have here basic molecules, the basic molecules are also positively charged. So we have the same charges of the surface and the compound, and therefore we have a repulsion situation. And that means that the interactions are reduced, and then the key value will be down because the retention is lower. Yeah. So, and that's pretty important to know that, because if you know the charge situation of your stationary phase and on your compounds, you can clearly predict how the behavior will be of your compound. And that is pretty helpful for the method development. So the last point is also the influence of the mobile phase, but the focus is on the organic modifier. And there is a model how you can handle that. It's called the solubility parameter. And there are clearly values for the defined different organic modifiers and also water. And it's also easy to calculate the solubility parameter of different mixtures. So using this model, it's what the most of you are aware on it, that the acetonitrile is a stronger eluating solvent. So if we have 100% of methanol, it's identical with approximately 78% of acetonitrile. And if we are looking on the THF, we are seeing that about 100% of acetonitrile is approximately 82% of THF. Yeah. So methanol is the lowest, is a solvent with the lowest elution power. Then comes acetonitrile, and THF is that one is the strongest. Going back to our D4 test, which we are using in our QC control, and we have had a standard eluent with acetonitrile water 58 to 42. And if we are using this model of this and calculate it to methanol, it would be 7 to 5 to 25, should give the similar results. And when beside this calculated ratio, we have also made some adjustments, which I will show you in the next slide. So what we have here is a standard C18 phase. And on the standard C18 phase, we have here the D4 test, as you have seen it before. And we have a really good separation. And going to methanol water, what we're seeing, we have a similar pattern here on this phase, but we have a slightly shift to lower retention times. If we are making an adjustment to get the same retention for the toluene, as we have done it here, we see that we have also the pattern are changing, and we are seeing we have an increasing retention for the toluamide. And that's due to the fact that also the standard C18 has slightly polar interactions, and which are supported by methanol, and therefore we have a slightly increase of retention of toluamide. Going now to a polar phase, in this case it's a platinum C18. It's one of the most polar C18 phases. And we see that immediately because the retention of the toluene is much lower, but the two polar compounds, the phenyl and the toluamide, they are good separated. And switching to the methanol water, which is calculated by the model, we see the separation is still good, but also we see the shift to the to lower retention times. And if we make also the adjustment to the same retention window for the toluene, we're seeing that we have also a big shift of the toluamide beside the toluene. So what we are seeing here is if we have a compound like the toluamide, which has a possibility of a polar interaction, we have a stationary phase which offering the polar interaction, and we have a organic a modifier like methanol, which are supporting the organic interaction. We have a clearly shift from, if we are looking from the standard C18, where we have the biggest distance of these two compounds going here to this situation, to the polar combination, then we are coming here close together. So using these three different possibilities, we have a clearly nice tool for the method development. So going ahead to the phenyl phases, so we have here the typical acetonitrile water situation, and what we are seeing is it's somehow in between the phases we have seen before. It's a little bit closer to the polar C18 phase. But if we are switching to methanol, what we are seeing is that the retention of the toluamide is really increasing on it. And if we are putting a little bit more water inside, what we're seeing here is the switch between the toluene and the toluamide. So what we have here, the possibility over if we are moving from acetonitrile to methanol, we are increasing the interactions between the p electron system of the phase and our polar compounds. Yeah. So using phenyl phases, you have the possibility easily to adjust the retention of the different compounds by using methanol or acetonitrile mixtures to put the peaks exactly at that position you want to have it. Okay, that was the overview about multi-selectivity phases and how to use them in method development.
All right, thank you very much, Jürgen, for your presentation. So we are open for questions. And once again, you can ask questions using the question and answer icon at the bottom of your screen. Please don't use the chat function. Or you can speak up after raising your hand. I've worked on a few questions during the presentation. There's one open one here. Maybe I'll just read this out to Jürgen. It says lactose and galactose coelute on aminopropyl phases, while on polymeric aminopropyl phases, better separation is achieved. Please suggest a column for this separation. I believe we have one, and there are various possibilities to separate saccharides.
Yeah, that's
so can you remember what that application requires?
I have to look which one is the best one, but it's a helic application, of course. So, and for the helic of you have the amino phases are the best choice for sugars, and which amino phase would be the best? We have the carbohydrate, different carbohydrate columns, so I have to look on the applications we have on that. it will probably better to do it offline later.
Yeah, I make a note on
that. One thing what it can do is standardly the acetonitrile is used as an organic modifier, and to increase selectivity, it's also possible to exchange a small amount of the acetonitrile by methanol to support the interactions. And I would make a test with 90% acetonitrile, 10% methanol, and going ahead with 10% steps. And then, of course, it probably can be separated on any amino phases.
Yeah, there was another question I already answered before. Maybe you want to add something to that. Let me see. When I find it again. Yeah, the question was whether you could use a phosphate buffer in Hilic as well as methanol as an organic modifier.
Yes, that's possible. Of course, it's always important to double check about the solubility of the buffer due to the fact that you are using very high concentrations of organic modifier, and you have always to check if your buffer is soluble in these high concentrations. So you get no precipitation when you mix it.
Yeah, is that also the question, the answer to the question whether or not you can use methanol?
Yeah.
Okay, I see no more questions in writing. Does anyone want to speak up? Okay, let's give a few more seconds. All right, so it seems that nobody else has any questions. In this case, I close today's webinar. Thank you for your attention, and you're always welcome to contact us by email or by phone later. All right, thank you very much. Have a wonderful day. Thank you.
Thanks.